Thank you very much, Hazel. I had totally forgotten about that. Okay, so let me start over then. All right, so to briefly start over here, the F statistic is the statistic we use for ANOVA. We're going to start doing a simpler test called the two-sample F test, of which ANOVA is actually just a complicated kind of two-sample F test. But the F statistic is what you get if you have two different normally distributed populations with the same variance, and you take a sample from each one of them. So you get one sample from one sample from the other one, and then you make a ratio out of their standard deviations like this right here, S1 squared over S2 squared. And then the F distribution is the sampling distribution that you get of that statistic, S1 squared over S2 squared. So they have two different statistics. So that means F distributions, unlike the other things we talked about, or the other distributions we talked about, have two different degrees of freedom, one for the numerator and one for the denominator. And they're both n-1, whatever the sample size is for the numerator and denominator. So one of the things you want to see is that since sigma 1 equals sigma 2, when we make this ratio right here, S1 over S2, like we would expect those things to be equal. Like the expected value of S1 is sigma 1, and the expected value of S2 is sigma 2. And so when we make a ratio out of this, the thing we get is 1, right? The expected value would be 1. It's not all the possible values, right? Certainly you can see like down here, you could have S1 much bigger than S2 if you're over on this side of the picture, or S1 smaller than S2 if you're over here. But on average, it's usually going to come out to around 1, which means that the mean of all the F distributions is 1. Yeah, I'll let you explain that in your own words down here. A couple other things. F can't be negative, and F distributions are all skewed to the right. So I'm going to let you guys, I have extra credit here for you to answer those for test 3. Just include that with your third test. If you want to answer those in your own words, and then just attach that to the test. It's not going to be, this isn't going to be printed on test 3. It'll be something you answer beforehand and just include with your test. Yeah, so that's F distributions. They kind of look like chi-square distributions superficially, but they're not. Remember the chi-square distributions mean is not always 1. It's the number of degrees of freedom, which if you remember from like the test of a single variance, that could be a pretty big number some of the time. So F distributions are all way over hugged up to the y-axis with a mean of 1. The way we find areas in F distributions is the same way we find areas in the other distributions. There's a CDF in your calculator. It's at CDF. You can go to, if you just go to second vars and then scroll to the bottom, there's FCDF. And the way you put it in is left and right, just like usual. You put in the left bound and right bound, and then 2 different degrees of freedom, numerator and denominator, right? And it goes in the order numerator, denominator. You have to put it in that order. So here's a little bit of practice for you.
Yep.
Try to use your calculator to find this area to the right of 2.45 on that F distribution. This is 17 numerator degrees of freedom and 23 denominator degrees of freedom. So see if you can do that in your calculator, and I'll type out the command in here too. So have a shot at it. Approximately equals must be in here. What the heck?
Oh, I thought it was minus infinity and 2.45. No, because you said to the right.
Did I say left?
So,
no, I said right.
Right. So right means like 2.45 is
2.45 and larger.
Oh, yeah. 2.45 and larger. Okay.
Yeah. So I'm asking about this. Right, so F kind of looks like this.
Okay.
Right, and there's 2.45. Oh my gosh, this is so hard to write with my hand. And I'm asking for that stuff, right?
2.45 skewed to the okay.
Yeah, that's what I'm asking for there.
So the answer is 0.0233.
Sounds about right.
Yep.
Remember, we're expecting it to be relatively small because the mean is 1, and this is 2.45, which is bigger, and so it should be a relatively small portion. Is that what you guys? Is that what the rest of you got? Asima and Maddie and Cole?
I'm still
Yes.
typing it in my calculator.
Okay. Yeah, give the other ones a shot too.
Yeah, that's what I got.
Cool. Oop, that's not what I meant there.
At 0.506.
What did you get there, Asima?
0.506.
0.506. Okay. So I have a quick question for you guys there, which is the one in the brackets. I said the mean was 1, and it is. So why isn't that number 0.5? Right, it's not exactly 0.5. Any ideas why?
No idea.
All right, so the basic idea is that remember that the mean isn't always in the middle. It's the median that's in the middle. The mean is, in this case, a little bit to the right of the middle because all of these are skewed to the right. And so you actually get a little bit more area to the left of the mean than you do to the right, which is what we're seeing here. Now, if I'd asked you to find the area to the left of the median, that would be 0.5, but the mean not necessarily. So yeah, don't forget this distribution is not symmetric; it's skewed. But that's basically right. And then for this one, right? So just be FCDF of 0.68 to what 3.19, 3.19 with 4 and 18 degrees of freedom, something like that. I should put some spaces in here.
That will be 0.577.
0.577. Sure, that sounds about right.
Yep.
All right, so you guys are okay with using FCDF then?
Yep.
All right, anyone, I should ask that different. Anyone not okay with using FCDF? Okay, so here's what we're gonna do. The most basic kind of test using F statistic, two-sample F test. So we're testing to see, so remember that an F test, all that does is, or excuse me, an F statistic is just a ratio of sample standard deviations. And so what we're going to do with our two-sample F test is see if two sample standard deviations are similar enough to each other that we can think of them as the same. So our null hypothesis in each case is that it's given in terms of variance, but if you write it in terms of standard deviations, it works fine too. That variances are equal in each case, and then the alternative can be that one is bigger than the other one's smaller than the other, or that they're just not equal to. Which it's pretty easy to handle, to be honest. We just make an F statistic out of the sample variances, and then find our p-value, which is just the area in the F statistic. So that's basically it. Yeah.
So there's no greater than or equal or less than or equal. It's just equal and not equals.
Well, so sort of, in the sense of the like greater than. You could write this as less than or equal to if you wanted, but it's the same math.
Okay.
And we're just going to be testing. We're really just going to be testing to see if they're equal most of the time. Now, to be fair, like here, let me put it this way. So let's look at number 3.
Okay.
You want to see if a newer machine is more precise in making nails of the right size than an older machine. So the old machine gives a sample of 48 nails, standard deviation of 0.038 inches. New machine has a sample of 53 nails with a standard deviation of 0.026 inches. And we want to see if the new machine makes more consistently sized nails than the old machine. So we want to see if the standard deviation for the new machine is less, because that's what more consistent means. Remember that higher standard deviation means more inconsistent or less consistent. So we want to see if the new machine makes has a lower standard deviation than the old machine, which is going to be like this one probably. So we could write this as greater than or equal to if we wanted to, but really it would be the same math. So I just wrote them all. You can do you can do it that way if you want. It's fine.
Okay.
So what I want to do is make an F statistic out of these variances. Or did I say standard deviations for an F statistic? I hope not. Oh, sample variances. Good. I did say variances. All right, good. Yeah, so we want to make an F statistic out of these variances. Now, we don't have variances. What we have are standard deviations.
Yep.
But we just turn them into variances by squaring them. Right. So what I want to do is first I want to write hypotheses. My hypotheses are going to be something like one of these. Right. I'm just gonna copy paste it. So my null hypothesis is that guy.
Sigma square 1. Is it a sigma?
Yeah, it's sigma.
Okay.
That the variances are equal. My alternative hypothesis is going to be that the variance of the new machine, which I'm going to call 1, is lower than the variance for the old machine. So I'm going to say 1 equals new machine, 2 equals old machine. And again, remember that more consistent means lower variance. So that's why I'm doing new machine is lower than the old machine. And so to do that, I'm just going to make a ratio out of that. I'm just going to take S1 squared over S2 squared. So S1 squared divided by S2 squared. And we do want to square these, and these are S's, these are not sigmas. And I want to say that that's approximately equal to, I unpasted my thing.
0.9.
I get that value. So I need to calculate that, right? I don't have a Desmos open.
0.90.
0.9?
T. 0.905.
0.905. Okay. 0.90. Is that right? That doesn't seem right. Did you square them? Or am I just remembering wrong?
Oh, I didn't square.
Okay.
My mistake.
By
It's 0.820.
I got 0.468. Cool.
I got 0.468 as well.
Yeah. 0.468. Why is it not?
I did
sigma
0.026
anymore?
squared over 0.038 squared.
Yeah, that's what I got too.
Okay. So I want to go to the left here because this is a less than alternative hypothesis.
Okay.
So I want to go to the left side. So I want to do FCDF of 0 up to 0.468 for my p-value. All right, and then I need to figure out my numerator and denominator degrees of freedom. Well,
So,
my,
so
go ahead.
47 and 52?
Yeah, 47 and 52, but in the other order, because I put
Near machine first.
S1 on top. I put the new one on top.
Okay.
Yeah, so 52 and 47. Oops.
Zero zero 0.0041. Jeff, I want to ask, why did it change from sigma squares to S squares?
Because, so these hypotheses are
Mhm.
about parameters, like always. Like, you know how we write our hypotheses for like a t-test about mu, or
Okay.
a z-test or a proportions test about p, the population.
Yeah.
But the data that we have is sample.
It's X bar and S.
Exactly, X bar and S. And so that's why we're using S's, because again, like we
Okay.
don't actually know what the population standard deviations are,
Okay.
but our null hypothesis is that they're the same. And so we can use an F for this, right? So we make our F ratio for all the possible, I want to say here, all the possible ratios of variances that we could get, given that sigma 1 squared and sigma 2 squared are the same. And then if they are not, which was what we're going to conclude here, since the p-value is so small, then that's where our conclusion is.
Got it.
So my conclusion is that this data shows that the new machine makes nails more precisely than the old one. All right, so I probably should say this.
So we're rejecting the null hypothesis because it's less than 5, right?
Yeah, less than 5%, right? So significance level of 5%. Yeah, that's 0.4%. It's significantly less than 5%.
Gotcha.
And that's all a two-sample F-test is. It's just you make a ratio out of the sample variances, use your FCDF to find your p-value, and there you go.
Okay.
All right, you guys want to ask any questions on that?
I want to ask if we can put like S2 by S1.
You can. If you do that, what do I
We need to change the degrees of freedom.
Well, yeah, you'd reverse them, but you'd
Okay.
also be going, so in this case, if you wanted to say sigma 2 is less than sigma 1.
Also, we'll just be
Go to the-
flipping.
Yeah, I'm just trying to think of which direction you'd be going. If you did S2 over S1, you would be going to the right in that case.
Okay.
If we wanted to test, say that S2 is bigger than S1, or that sigma 2 is bigger than sigma 1. So just be careful with that. So here's the way you want to think of this. The thing that I was just doing in my head was, if the alternative hypothesis is that say sigma 2 is bigger than sigma 2 is bigger than sigma 1, then if we do sigma 2 over sigma 1, we would expect to get a bigger number than 1. So I'm going to go to the right. Right? And same way the other way around. If we thought that sigma 1 was bigger than sigma 2 and we wrote sigma 1 greater than sigma 2, and we did sigma 1 on top, we would go to the right. So you have to ask yourself, if you're going to do them in some order that's not sigma 1, then sigma 2, have to ask yourself, what does my alternative hypothesis suggest? If the alternative hypothesis is true, where would I expect to find my F ratio?
Okay.
And in this case, because if our alternative hypothesis was true and sigma 1 is smaller than sigma 2, and I put sigma 1 on top, that would give me a fraction that is smaller than 1, so I'd want to go to the left,
Okay.
right? Whereas if I'd done it the other way, I'd want to go to the right.
Right.
Does that make
Okay.
sense, Hazel? Because you can do it either
Yeah.
way, you just have to be careful with it.
Yes.
All right, so that's 2-sample F, that's all it does. One of the things, so do you remember when we were doing 2-sample hypothesis testing and we did a 2-sample t-test, and one of the options at the bottom was pooled or unpooled, and I just said always use unpooled?
No. Yeah.
The reason I said that is to use pooled, what you should really do is this 2-sample F test, because pooled will tell you whether or not your standard deviations are close enough to each other to be considered the same, which is what pooled is doing. And that just seems like extra complication we don't need there for a marginal gain. So that's why just continue using unpooled. If you want to do this, I might ask an extra credit question on the test about pooled versus unpooled, and then checking to see if they're the same using a 2-sample F test. We'll see. All right. So ANOVA, like I said, is basically a fancy use of the 2-sample F test. I don't want to say fancy because it really is 2-sample F test, but the variances that we're choosing are not intuitive. Like, it's not obvious what they would be. So firstly, before I go into any of that, let me talk about what ANOVA is. So ANOVA is a test that will check to see if several different means are the same or not, or the several different sample means come from populations with the same population, I should say. And that's what ANOVA is for. It's like a 2-sample t-test, except it's for multiple samples. So you can use it for several different samples, and it'll just check to see if they're all equal. That's all it does.
Oh.
So again, the idea of ANOVA is to determine whether several population means are the same or not. That's what it's doing. So anytime you want to find out if several population means are the same, 3 or more, you do an ANOVA test. That's what it's for. So we need 3 conditions for this, which we'll return to later. You have to have each sample randomly selected from a normally distributed population. Samples all have to be independent, and the populations have to all have the same variance, because we're going to use pooled, essentially. We're going to return to this. A thing that I wish I had been doing more along the course is having us check assumptions. And so we're going to check the assumptions for ANOVA. It gets a little bit complicated, but but we'll do that. Okay. So here is what the assumptions are. Assuming we have k different populations. So for our example, k is going to be 3, right? K is just how many populations there are. The null hypothesis always looks like this. All population means are the same. You can write it as all population means are the same, or you can write it as mu1 equals mu2 equals up to mu k. And then the only thing that the alternative hypothesis does is it will tell you that one population mean is different from the others. It does not tell you which one. And we're not going to really go into how to figure that out. It's not super hard, but I want to make sure that you guys know how to do ANOVA before we worry about that. But that's all it tests, is one is different than the other ones. So if even one population mean is different than the other ones, that you'll end up rejecting the null hypothesis, right? Even if, like, let's say you have 10 populations, 9 of them are the same and 1 is different, you still end up rejecting the null hypothesis.
So there's only one alternative, and it's like at least one population mean is different from others.
Yeah, in fact, the hypotheses for ANOVA are always the same.
Same.
Yeah,
Okay.
these are always the same. There are what are called post hoc tests that you can do to figure out which one is different. I'm not going to worry about those so much. I'll show you how to do it, or I'll tell you, describe to you how to do it. And if you watch the crash course video on ANOVA, they show you how to do it. It's not actually all that hard. You just do pairwise t-tests. Or you can use confidence intervals too. Anyway, so here's the basic idea. And this is where it gets a little bit fancy. We're going to have two kind of, the variances that we're going to get are going to be, all right, so let me back up a second and do the setup. The setup for ANOVA is this. You have a bunch of different samples from different populations, and you want to see if their population means are all the same or not. Oh. All right, there we go. Okay, you have several different samples, and you want to see if they come from populations with the same mean or not. So each of those samples has a variance and a standard deviation. And so what you do is you find the average variance of all of the samples. So you find that, like, you find the variance of each sample and you average them. You actually do a weighted average, but we're not going to worry about the specifics. And that is called mean squares within. And it's called within because it's within the sample. It's the variance within the samples all averaged together. Mean squares just means variance. Variance is actually a kind of mean squares. The other thing that you do, the other variance, so that's one of the variances that we're going to use. That's going to be the denominator variance. The numerator variance is called mean squares between. And what you do with that is you take each sample mean, so each x1 bar, x2 bar, x3 bar, and you throw them all into a set, and you find the variance of that set of the sample means, and that is your numerator variance. So that's what this is saying right here. Now, they're sometimes called factor and error. Like when you do it in your calculator, you're going to see factor and error and not between and within, but they're just different names for the same thing. So the reason we compare those is slightly complicated. So here it is. If what we're testing to see is if the means are far apart or not, right? If the sample means are far apart, we're testing to see if the population means are the same. So we want to see if the sample means are close together. Close together means small variance. And so if they are close together, MSB will be small. But the thing we want to compare it to is there's sampling variation for each of the samples, right? So even if all the means are the same, we're not actually going to get all the sample means being the same. Even if all the population means are the same, the sample means that we get are going to be a little bit different just because we get different samples. So the variation of the samples is about equal to how far apart the population means should be. So if the population means are a lot farther apart than the variance for the samples would indicate, that means that the population means are probably different from each other. And I 100% understand if you didn't follow that logic. You're really going to have to think about it. Like this is, in my opinion, this is the most logically complicated thing that we do. Now, luckily, it's not super, super important that you understand that logic, right? You can just trust me that the ratio you want is MSB over MSW for your F statistic, and then we do a 2-sample F test on that. And it's true. But I would encourage you to think about, okay, what does it mean if MSB, the variance of the population mean, or the variance of the sample means, is significantly larger than MSW, the variance of the individual samples. And what does it mean if MSB is smaller, for instance, than the variance of MSW, or than the variance of than MSW. So I'll let you think about that. That is true. The explanation I gave you is the right one, but it does take some thinking. Okay, so let me talk about degrees of freedom and then we'll do a test. So the degrees of freedom for MSB, remember that MSB is the set of the sample means. So there's one per sample. And so we have K of those since we're comparing K samples. Remember that we're comparing K samples and we have K different populations that we're drawing from. So we get K minus 1 for the numerator degrees of freedom, just one less than that. For the denominator, because we are effectively pooling all of the samples into one big sample and finding the variance of that, that really is essentially what we're doing here, then we have the total number of samples, or not the total number of samples, the total number of, I guess samples is the right word there. The total sample size, essentially, minus 1 per sample, which is n minus k. So numerator is pretty straightforward. We have k things in our set, so we have k minus 1 degrees of freedom. The denominator is the average of all the samples. So each sample has this n sub I minus 1 degrees of freedom. So like n1 is the sample size from sample 1 minus 1. So the first sample has n1 minus 1 degrees of freedom. The second sample is n2 minus 1 degrees of freedom. Then we add all those up because we're doing a pooled thing. This is why all the variances have to be the same. So you end up with this, which is n minus k.
N minus k. Okay.
Yeah. Now you don't actually have to do this degree of freedom by calculation by hand. Basically, it's all going to be in the calculator. But I want to show you like where it's all coming from when we do the test.
Okay.
So then what we do is we just make our F ratio of MSB over MSW. Remember that MSB is our variance of the sample means, and MSW is the average variance of each sample. And those are the things that we're comparing to find our p-value. It's just a two-sample F-test again, just like we did before. So
What's MSW again?
MSW stands for mean squares within. It's the average variance of the samples. Right? You find the variance of each sample and you average them all together. Now, I will tell you this. If you try and do this thing by hand, it is a huge mess. Like if you look in the book, and every book I've ever seen does the same thing, they don't even give you the formula in like one big formula form because it's too big. They give you the formula in this form, MSB over MSW, and then you find the formula for MSB, which is kind of a mess, and the formula for MSW, which is kind of a mess. And so like if you just did this formula out, it would take up like an entire page, or not an entire page, but an entire line.
Okay.
We're not going to do any of that. What we're going to do is use the calculator because that's easy. And it's really what I want you to concentrate on here is like, what's the meaning, and did we check the right assumptions, etc. Just like you would do real statistics. Like this is what real statistics looks like. It looks like you check all your assumptions to make sure that the test is valid, and then you have a computer do all the work, and that's what we're going to do. So we're going to do a really simple ANOVA here. We're going to do number 4. So products in supermarkets are typically displayed on one of 3 levels, top, middle, or bottom. We're assuming some kind of large shelves here. I know there's usually 4 or 5 shelves on a supermarket, but we're simplifying a little bit. We've got a bakery in the supermarket, and we're going to see what the sales look like on the top, middle, and bottom shelves. And we want to see if they are equal, if the mean sales on each shelf are equal or not.
Okay.
So here we go. We've got sales from the last 6 months for each shelf, right? Top shelf has these sales for the last 6 months. Middle shelf has these. Bottom has these. Oop, that didn't do what I wanted to do. And we just want to see if the mean sales for the shelves are equal. And just looking at it, it's a little bit hard to tell, but it kind of looks like maybe yeah, they're similar.
Yeah.
For sure, they're similar. I would say that the middle looks like it might be a little bit bigger, like they're almost all in the 60s, and the bottom has like 40s and 50s. So like you said, they're similar. It's a little hard to tell if the averages are equal or not. The middle looks like it might be a little bit higher, but with only 6 data points, we want to find out if that's significantly higher, right? Which is what we're going to test. So here's how you do this. In your calculator, put all that data into lists, right? You just want to L1, L2, L3, 1 list per population. So just put top and L1, middle and L2, bottom and L3. And so I'll let you type there, but go right ahead. Oh, that's not what I was trying to do. What am I trying to do? Bring out chat. Okay. Do you guys see a little like thumbs up thing or something like that on your Zoom, like under the chat, I think?
Yeah, we can do reactions like this.
Oh, cool. Yeah. So whenever you're done, just hit the thumbs up so I can see. Great, because I can see it on your pictures. Cool. Maddie, that
Where's that
feature
feature?
is by chat. Like I think it's
By-
under the chat menu.
If you're on the laptop, then I think it's like beside record. There's 5 things like participant, chat, share screen, record, and reactions. You just
Yeah, it's one of the
press reaction.
reactions. Yeah, it's a reaction.
Okay.
Cool. All right, great. Everybody's done. All right, so then you can do these things. So here's how you do an ANOVA test. It's pretty simple. There's just a button for it in tests. Just go to stat tests, and then the bottom one is ANOVA. And then it won't give you the normal screen like it does, like it usually does. It'll just put ANOVA parenthesis on the home screen, and you have to type in the columns that you used. So
Okay.
this is what I got when I hit ANOVA. I got something that looked like this, except it just said ANOVA left parenthesis, and then I typed in L1, comma L2, comma L3 close parenthesis.
Okay.
And then when you get that, go ahead and hit enter, and it'll bring up the screen right here. The next two pictures, these two pictures, by the way, are all one screen. It's just that it's you scroll down to get the second picture.
Yeah.
All right. So once you do that, you got all the important stuff that you need. It gives you all of the things that that we talked about calculating. It gives you MSB and MSW. It calls them factor and error, MS factor and MS error, which is pretty common. Like that's factor is between and error is within.
Okay.
So MSB here is 122.65 and MSW is 12.86. It finds the degrees of freedom for both of them, and it tells you what the sum of squares is as well, which we're not going to use. You can potentially use these in an ANOVA table, but we're not going to. MS is just SS over degrees of freedom. So this 122 is 245.3 divided by 2. And this 12.86 is 192.96 divided by 15. That's all those things are. The thing we care about, though, primarily is the p-value, which is this guy right here, 0.02. And there's our F statistic as well, 9.53. That's pretty much it. Like that's how you do an ANOVA test. There's one more thing on here. It's SXP. SXP just means you remember how I said MSW is the average variance, or is the average of all the variances of each sample. SXP is the standard deviation. It's just the square root of MSW. If we did 12.86 and took the square root, you'd get 3.586.
Yeah, so like
no, go ahead.
The F value 9.53 is like we take the MS factor divided by MS error.
Yeah, that's correct.
Oh, okay.
Yep. Yeah, we don't have to. The calculator just does it for you, but yes, that's what it is.
Okay.
This number right here, this 3.5866, is useful if you're making confidence intervals for ANOVA, because you end up using this for your standard error, to calculate your standard error. For us, not that useful. We're mostly just interested in the p-value and the conclusion.
The SS are the S squares, sigma squares?
No, SS stands for sum of squares. It is effectively the numerator of the variance.
Okay.
Which you might ask yourself why you wanted to know that. let me recommend the crash course video to you where they talk actually quite a bit about the SS's and what they represent. They're basically just how far away from the mean the samples were. It's the square deviations from the mean, basically, is what these are, that when you add them all up. Yeah, so there's another thing in ANOVA called sum of squares total, which is calculated a different way, but is the sum of SSB and SSW, and you can use that to check to see that you've done the calculation properly, which is completely unnecessary because we're having a calculator do it. We're just going to trust the calculator to do the math.
Okay.
But, so as far as I know, these have no use for us because we're just doing them on calculator. Where do I want to say? So see if you can use what we just did to write appropriate hypotheses, determine if you should reject the null hypothesis, and write the appropriate conclusion. All right, so basically just now that we've done it on the calculator, I want you to say, okay, well, I did this on the calculator. Let me write down the answer.
And we write down the values, right?
Write down the values. What do you mean?
Like, because we did it on the calculator, like the F value and P value.
Oh, yeah. Like on a test, I would appreciate seeing like F equals P equals, and yeah, like you don't have to put in all of this nonsense for an ANOVA test. Just like I did an ANOVA test. I got F equals this, P equals that. That's fine. Oops. There. Oh, I'm not going to do that.
So like our conclusion would be there is a significant difference between bakery sales depending upon the shelf in terms of the items they are displayed on, right? Because we reject the null hypothesis.
Yes, yeah, that's exactly right. Yeah, p-value, so reject hypothesis, conclusion, the So yeah, something like this.
Okay.
You can write as mu1, mu2, mu3 if you want. I prefer to be more descriptive. I'd say like mu top, mu middle, mu bottom. Doesn't make any difference really. Like they're both fine. I do want to say that don't write this as just at least one of the means is different than the others. Like I really want to avoid the sort of like copy paste the same thing every time mentality because it makes you it sort of allows you to turn your brain off. I don't want you to do that. What I really want you to do is say what you mean in like the plainest terms you can. So for me, at least one of the shelves has different average sales than the other shelves. Right, because that's really what we're
Okay.
testing. And then this is plenty as far as I'm concerned, as far for showing your work, right?
Yeah.
Like you get an F value, P value, if you want to do like ANOVA test, something like that, right? Just to let me know what you did, so that I can see what you did on the test. Right? You don't have to write in MSB and MSW and SXP and all that stuff. Like you can just ignore that. The thing we care about is this.
Okay.
And then write a conclusion, and then that's it. So, yeah, what do you guys want to ask about? Because that's basically how you do. That's the basics of doing an ANOVA test.
I think I got it.
Cole, Maddie, and Asima, you guys okay with this?
Yeah, I think so.
Cool. All right. Well, so one other thing I want to show you about ANOVA is how to check the assumptions. So if you recall, there were 3 assumptions that we were making to do an ANOVA test. These 3. Right. Each sample is randomly selected from a normally distributed population. The samples all have to be independent of each other, and the populations all have to have the same variance. Yeah. So those are the 3 things that we need in order to do an ANOVA test like this. So here's how we can check those. Oops. There we go. One of the things I do want to mention is that ANOVA is kind of sensitive to assumptions. So like if your assumptions aren't met, the ANOVA really isn't valid. Like it doesn't work very well. It doesn't necessarily give you correct probabilities, or you don't necessarily reject or accept or reject the null hypothesis correctly unless the assumptions are met or very close to met. So here's what we got. Each sample must be randomly selected from a normally distributed population is our first assumption. Now, we don't really have any way to tell if the normal selection was done unless it says something about it in the problem. So in general, we're probably just assuming that this was done fine. We're just going to have to trust the researcher to have done it okay. We can check to see if the populations are normally distributed by making a QQ plot. I don't know if you guys remember that from 2 sample. Yeah, from 2 sample. Like we did in paired T's. How to do a QQ plot. I'll talk about it again here. But that's how we can check to see if the populations are normally distributed. Each sample must be independent of the others. Again, we don't really have any way to check this. That's kind of up to the researcher. So we're just gonna have to trust this one. And then each population must have the same variance. That we can check. We can do a 2 sample F test to see if they have equal variances or not. So that's what we're going to do. We're going to make QQ plots, and we're going to do 2 sample F tests to check variance or check equal variance, and then that's it. Okay. So here's how we make QQ plots. Right, you go to stat plot and choose one of them, and change it to the 6th option like this. Right, so this guy was the QQ plot in stat plot. Stat plot is the second function of y equals, in case you forgot. Then we go turn on that plot and graph it, and we're looking for a straight line basically. So pick whichever plot you want. I did plot 1. You don't have to. You can use plot 3 or whatever if you want to. I usually leave plot 3 as a QQ plot in my calculator, just so I don't have to reset it every time because I don't use plot 3 all that much. And
Really
plot 1 as scatter plots. I'm sorry. Say it again, Cole.
How do we graph it? So once we have the 6th graph selected.
So change it to the data. So we're gonna do one of these for each sample. So one for L1, one for L2, and one for L3. So once you've got it set up like I have in this picture here, go to y equals and turn on plot 1 and make sure you don't have any other stuff plotted there.
So plot 1 is our L1, right?
Well, the way I've got it is plot 1 is L1. You can change plot 1 to be whichever list you want. So so for this one, this is the one I did when I did L1. This is the one, you can see it's a different plot. All I did was change data list to L2 for this one, and I changed the data list to L3 for that one.
Hold up. So when let me show you what I'm seeing right here. I don't know if you can see that, but I just have
Oh no,
L1.
delete the L1 from your Y1. That's not what you want.
Okay. What do I
Yeah,
want in there?
Nothing.
So,
Nothing. Just have plot 1 on and that's it.
Oh, okay.
press second Y. We need to go to stat plot.
Oh, I think you already did that.
Yeah, I did that. And then Y equals and then just graph.
Yeah, just hit graph. And you probably won't see anything. It probably looks blank. So you want to zoom stat. You got to go to zoom and zoom stat like this. Because it's probably looking at the wrong area on the graph.
So zoom.
And then zoom stats 9.
Okay, gotcha.
Yeah, and then you should see this, I think.
Okay, yeah, gotcha. Thank you.
And what we're looking for here is an approximately straight line. This line is actually very straight. This is about as straight a QQ plot as you'll ever see. Which, if it's relatively straight, that tells us that the distribution is, or the population distribution is likely normal. It's at least plausibly normal, we'll say.
Normally distributed. Right.
Yeah, that's what we're looking for. So one of the things I should mention is, remember I said this is basically a t-test, but for more things. That means that we want to meet the requirements of the central limit theorem, which is either normally distributed population or large sample size. Well, our sample size is 6, right? That's not anywhere near large enough. So what we want is to see that the population is normally distributed. That's why we're doing this. Because otherwise the central limit theorem doesn't apply.
Okay.
Right, and then you do the same thing for L2. If you just go to stat plot and change the data list to L2, and then graph and zoom stat again, you get this. And same thing for L3. And if you do that, it's reasonable. Like these are all quite straight as QQ plots go, and so it's reasonable to think that all the populations are normally distributed.
Okay.
That's the way you can check to see if the populations are plausibly normal.
So if one of them was like not straight at all, then it would not be normally distributed.
Yeah, you would think that population might not be normally distributed. Now, what you do in that case, after you've done you've done the ANOVA test, right, and you're going to check to see if it was valid, you might want to put a little caveat on, like your conclusion would be something like the different bakery shells have different average sales, but it's not clear that this ANOVA is entirely valid, right? Let's say two of the 3 populations look normal, but the third one does not look particularly normal. And so that calls this conclusion into question. So that's usually what I end up doing with these ANOVAs that where the assumptions aren't necessarily met all that well, is say something about it in the conclusion. Like, here's what we get from the conclusion. The p-value suggests this, but this assumption was not met as well as we would like, and so I consider this conclusion questionable. Now, if your p-value is really, really small anyway, like if it's, like 0.00005 or something like that, maybe that's so far so far below the significance level that you're still willing to accept the conclusion, right? That's a reasonable way to put it, but you really do want to at least mention it at the conclusion. Okay, this assumption wasn't all that great, and this other one was fine. Right. So anyway.
Okay, gotcha. Thank you.
You're welcome. So in this case, it all worked out pretty well. The assumptions all look pretty well met, or excuse me, the normality assumption looks pretty well met. And then we also want to test to see if the variances are equal or not from the 3 populations. And so we can do a 2-sample F test. Now, we don't have to do all the combinations. Like I don't have to do 1 and 2 and 1 and 3 and 2 and 3. All I really have to do is find the 2 that are farthest apart and do a test on that one, and do a test on that pair. Because, so here's what I got when I went and did 1 variable stats on all 3 of these, and I got the variance for the top was 3.9, or excuse me, the standard deviation for the top was 3.95, standard deviation for the middle was 3.7, and standard deviation from the bottom is 3.05. Obviously, those are different numbers, but what we really want to check is, are they far enough apart that it makes us think the population variances are not equal, right? Because these are just sample variances, or sample standard deviations. So a thing I kind of glossed over earlier is that we only really need to do the biggest one and the smallest one. Because if the biggest one and the smallest one, so if this and, oh gosh, do this. If that and that are close enough to each other that we're thinking that they're equal, or that their population variances are equal, then it's pretty clear that this one that's in the middle is also going to be considered equal to that.
Yeah.
Right? They're sort of squeezing it between these other two. So we really only have to check the biggest and the smallest ones, because what we need all the population variances to be equal. So if the ones that are the farthest apart are considered equal, then it's perfectly reasonable to consider all the ones in the middle equal too. So we can do a bunch of two sample F-tests, but we only really need to do the biggest and smallest.
Right.
Yeah. And so that's what I did. So I did one variable stats on all three lists, and then just wrote down the standard deviations for each one. And then I want to do a two sample F-test on these two standard deviations. Now, we could do it just like we did at the beginning of the worksheet, right? We find S top squared over S bottom squared, and and then we do a not equal to hypothesis test. Your calculator will also do that. It actually has a two sample F-test in it. So I might as well use that and use this as an excuse to show you how to do these, right? So if you just go to stat tests, there's two sample F-tests near the bottom. And if you wanted to, you could do stats when you get to two sample F-test and just use 3.95 and 3.05 and do not equal to, and that would be fine. But we happen to have the data in here already.
Yeah.
Right? So I'm just going to do data. That was for the top and bottom were list 1 and list 3. So I just did data instead of stats. You could totally use stats as well.
Okay.
Right, and you can see it actually tells you in the results screen what the standard deviations were. They were the ones that I said, 3.95 and 3.05.
And then which one do we look at, like, to make the assumption?
You mean to answer question 5 here?
On, like,
Do you mean for the
No,
two
I mean,
sample
like,
F-test, or what are you talking about?
if the assumptions are reasonable or not, like while
Yeah.
doing two sample F-tests.
Oh, so this refers to all three, right? So that's referring to all three of these assumptions, or at least the two that we checked, right? The normally distributed population and the equal variances.
I mean, like for the QQ plot, we can tell if the line is straight or not, like if the assumptions are straight, if the assumptions are true.
Here, I would say something like this. From the QQ plots, we can assume that the populations are normally distributed. QQ straight. From the two sample F-test, we can assume that all population variances are equal. Oh, by the way, I should talk about this. Two sample F-test. You guys see that the p-value here is 0.58?
Mm-hmm.
And so that's going to make us want to not reject the null hypothesis. And remember that for a two sample F-test, our null hypothesis is always that sigma 1 equals sigma 2.
Yeah.
So we're thinking that the variances are equal. That's what we're thinking for the top and bottom.
But yeah,
top.
That was my question. You just answered my question.
Oh, that was your question. Okay.
Yeah.
Yeah. Okay, good.
So I'm sorry, can you go over that again? That threw me off.
For sure. Yeah. Sorry. I just realized I had done that kind of fast. I was just assuming you guys knew exactly what this meant. So we do the two sample F-test, right? I use data from L1 and L3. This was the top and bottom shells.
Yeah.
And I have an alternative hypothesis of sigma 1 not equal to sigma 2. So my null hypothesis here is that sigma 1 squared equals sigma 2 squared. I need to make these sigmas. These are not S's. These are sigmas. Right. So my null hypothesis is this: is that sigma 1 squared equals sigma 2 squared. My alternative hypothesis is that they're not equal. Right. That's what we put here. What's that? This, but not equal to. Oh no, I've messed up. Hang on. That one. Right. So those are the hypotheses that we're making. And then when you look at the two sample f-test, it tells us that our p-value is 0.582. So what does that tell us we think?
So we accept it.
Yeah, we're going to accept the null hypothesis that sigma 1 equals sigma 2, or sigma 1 squared equals sigma 2 squared, just to say the variances are equal, right? That's what we were checking for. That was the third assumption here. Each population must have the same variance. And the two sample f-test we did indicates that the variances are the same, which is what we wanted to see. Right, so p-value of 0.58 means we think the variances are the same. So from two sample f-test, we can assume that all population variances are equal.
Okay.
We cannot check if the samples were drawn independently, nor can we check if they were trust researcher. Right, we weren't there for the choosing of the samples, and so we don't know if it was done properly. So we're just gonna trust that it is. Yeah. Again, if you were doing this in real life, like if you were really checking over somebody's work, you wouldn't just trust. You would ask them, like, how did we get these samples? Like, how did you determine them? Oh, you took them all on the same day? Well, those are probably not independent. That's not a good idea. And that's sort of it. Like, that's all there is to ANOVA. I said I would talk about how to determine which of these is different. Like, that's a thing that we can do here. Our conclusion was the bakery shelves have different average sales. So the natural question is, well, okay, which one is different than the others? And so what you would do for that is you could do a two-sample t-test on all the pairs, right? You do a two-sample t-test on top and middle, and a two-sample t-test on top and bottom, and a two-sample t-test on middle and bottom, and get results for each one to determine if you think those guys are equal or not. And that can usually tell you which ones are equal. Like, so let's say we get top and bottom come out to be equal, and the middle comes out to be not equal to both of them. Well, that would tell you the middle's different, and it's different than the other two. I'm not going to ask you to do that. It's kind of a little tedious, to be honest.
Two sample t-test or two sample f-test?
Two sample t-test, because what we're testing are the means equal, and that's a t-test to determine if two means are equal. Two sample f-test determines whether two variances are equal.
Okay.
Yeah, so it'd be a paired, or it'd be a two sample t-test. You can also do it by making confidence intervals for each group and then seeing where they overlap, and any one that doesn't overlap with the others is different. But again, that's not something I'm going to ask you.
How do we check for two sample t-test?
Oh, for two sample t-test, you just do two sample t-test on all the possible pairs. So in this case, there's three possible pairs, right? Top, middle, top, bottom, middle, bottom. Right?
So is it pool or unpooled? Like it's pooled,
For that, you
right?
can use pooled. We actually check pooled. That's what the two sample F test is checking. You can use pooled. So you would do pooled in that case. It actually doesn't make that much difference. Pooled
Yeah.
versus unpooled, the math, or it's only a minor gain in accuracy for pooled. But if you were doing two sample F tests, you do pooled.
Okay. And then they will give like the mean is equal or not, right?
Yeah, exactly.
Like,
Means
mean
equal or
one
means
is
not
equal.
equal to. Yeah. So you just check.
So
Again,
like,
let me refer you to the crash course video for this. They actually run through an example of that at the end.
okay,
I'm not going to ask you to
Okay.
do that, but if you want to, if you want to learn how to do
the
it,
check. Okay.
yeah, that's what you do. It's not particularly hard. It's just it just adds some extra tedious steps.
Okay.
And that's kind of it.
Can like not one, like can like two or more, two population mean can be different?
Yes. Yes.
Okay.
So that's why I wrote the conclusion right like this, right? The different bakery shelves have different average sales. We actually don't know which one or which ones are different from each other. Maybe all three are different from each other. But yeah, if we wanted to test, we could do a post hoc test.
Okay.
If we wanted to find out which one it was, we do a post hoc test. The homework doesn't ask you to do that. I won't ask you to do it on a test. But if you want to do it, it's not a particularly hard. It's just kind of a few extra steps.
Okay.
And that's all I had on ANOVA. You guys are welcome to ask whatever questions you want to go with this. Not even necessarily about ANOVA, but about older stuff if you would like.
I
If you
don't know
don't have,
if
what's that?
I don't know if Asima and Maddie has questions, but if possible, like for the remaining time, I think Cole and me, we want to go over like this for two sample testing and chi-square.
Okay, that's fine with me.
Yeah, two sample testing would be awesome.
Maddie and or Asima, would you like to ask any questions? And I tell you what, why don't I start doing this for two sample and chi-square, and then if you figure out, oh hey, like maybe you want to start the homework on ANOVA, for instance, and then you get part of the way in and realize you have questions, you could just ask questions, and that's fine. We have 45 more minutes. We have plenty of time to go over stuff. So if you have questions now, go ahead and ask the questions now. And if you don't have questions yet, feel free to jump in when I
Just
have a
pop in,
pause and
yeah.
just say, like, hey, can we go back to ANOVA for a minute? I want to ask about this other thing. Let me get my two sample and chi-square up.
I have a question from linear regression.
From linear regression. Okay, so let me get all of these things up, and then maybe we can answer a linear regression question first before I just go over all of chi-square and two sample. I think it would probably be quicker. Is this what's sharing? I can't tell.
It's sharing the.
I think it's still sharing.
Stuck.
It's still sharing
No,
the.
it's
Well, it's not stuck. It's just I haven't changed it yet. Sorry, so this is linear regression. So what did you want to ask about in linear regression, Asima?
Question number 72, I think E or D.
Okay, so let me get the book
From the homework.
Yeah, that's what I figured. 72. Minimize that. So this is the book. Fit one page here. And this is linear regression, so it's chapter 12. Yeah. 72. So this guy right here. Let's do. Whoop, where's my Zoom menu? Let's do like 150. All right. So we've got this stuff. Okay, so gold medal times for every other Summer Olympics for the women's 100-meter freestyle swim. And we get these. And you wanted to ask about which one? Okay, so we want to use the least squares line to estimate the gold medal time for the next Summer Olympics. So I'm going to assume
this
next
is not
summer.
the question. I think it's 7.
Did you say
You
72?
go a little bit down.
Is it
In
73?
my book. It's not 74 maybe.
Is it?
Oh,
Did
it's
you
not the
use?
same from the book.
Oh, is
like-
this one of the ones where the book and the like
Yeah.
online thing are different?
Yeah.
Oh, that's super annoying. Okay, so it's going to be like 73 or 71 then?
The height of notable tall buildings in America.
Height of notable
Yeah,
tall
that's-
buildings in America. Holy cow, where's that? Is that this? No. What? Oh, this one right here. Okay.
Yeah.
All
That's
right.
it.
74.
And then you
All
gotta
right.
let people
Oh
know.
my God, this book. I'm sorry. I'm just gonna have to switch away from this book. Anyway, so here's we got the height and the number of stories. So certainly it seems like these things would be related, right? The number of stories, the building, and how tall it is. So hopefully they come out to be that way. So you wanted to ask about I. Based
Question
on
number say F.
F. Based on the data, is there a linear relationship between the number of stories in tall buildings and the height of the buildings? So the thing that you want to check is what was the p-value that you got when you did Linreg t-test? Because remember, that's what that the t-test is checking is there a linear relationship is the test, right? It's the beta and rho equals 0 thing. That's the way that we're checking it, but you want to read that as, are these linearly related or not? So what,
Yeah.
yeah, so you probably,
0.0004.
okay, so it's tiny is what you're saying. Like the p-values are really small. So that would mean that they were related. Because remember that what you're doing there is, let me call up this. What you're doing there is this. Whoop, the heck? This hypothesis. Null hypothesis is that the, what am I trying to say here? The variables are uncorrelated, and the alternative is that the variables correlated, right? We look at this as beta and rho equals 0, and beta and rho are not equal to 0 for our hypotheses. But the way you want to think about those is this: that beta and rho equals 0 means the data is uncorrelated, the x and y are uncorrelated, and the beta and rho not equal to 0 means that they are correlated. And so if you got a p-value of, what'd you say, like 0.0004 or something like that, then that would make you want to reject the null hypothesis and accept the alternative that the variables are correlated. That's how you would check F. Is there a linear relationship? Yes, there is a linear relationship. They are correlated.
And Y is
Y is what? I'm sorry, I didn't understand that question, Asima.
I have to. So why the linear? I have to see the question. You said yes, right? And then
Yeah, they're correlated. That's what it appears. Let me get Desmos going here. Oh, whoa! What the heck? No. Yeah, just. Oh, computer, what are you doing? So what do we have here? I want to insert a table. So I'm getting so the x's go from like 200 to 1200, and the y's go from like 20 to 120, something like that. Yeah.
So on the homework, is it okay if we just do like a rough sketch of the graph, since that's like what it's asking for?
Oh, you mean like for the regression homework?
Yeah.
Yeah, that's totally fine.
Okay, cool. So I just kind of quickly sketched a graph.
Yeah, like if you like, I would recommend graphing it on your calculator so it's easy to tell what the graph looks like, and then just kind of
Yeah,
going
yeah,
down.
that's what I did.
Yeah, it's totally fine.
Cool.
Asima, did I answer your question, or was there more you wanted to ask about this? Because for F, we're just checking. Oh, sorry. I'm sorry. Say it again.
Can you look for question number I too?
Sure. Based on least squares line, adding an extra story is predicted to add about how many feet to the building. So let me share my Desmos screen again. I have something that looks like this. Right. And so what you want to remember is that, wait, we said adding an extra story is predicted to add how many feet? That's not what? Oh, these turkeys. Stories as the independent variable and height as the dependent variable. Oh, I did it all backwards. Shoot. Whoops. Let me try this again. I used the wrong thing for X and Y. I was trying to do it too fast. Let me. Yeah. So they wanted stories as the independent variable and height as the dependent variable, not the other way around. The way I did it was to use stories as dependent and height as independent, which really doesn't make a lot of sense. So let me type it in again real fast. All right, add a table. Add a table. So I guess instead of adding a table, let me do this. The thing that they're asking about, I'm sorry, say that again, Cole.
Sorry, I was just want to intervening. Would the basic idea behind it be like, basically your X would just be 1 to your equation, and so then so in your equation y equals mx plus b or whatever, you just set x equal to 1, and that would be
No, not exactly.
okay.
That would work if the y-intercept was 0, which it's not.
Okay.
What you want to do instead is just look at the slope. Because remember, this was the thing that I talked about last time on linear regression. Remember that the slope is how much y increases when x increases by 1. That's literally what the meaning of slope is. And so the question I is really just asking, what's the slope? What did you get for your slope, by the way?
11.758.
11.758. I am getting 13.6, unless I'm doing it wrong. Anyway,
I did it like from the calculator, like from the
yeah.
line.
No, I'll just use yours. You said 11 point something.
758.
758. Okay. So what that means is that when X increases by 1, Y increases by that much, by 11.758. That means that if the stories go up by 1, which is X, then the height goes up by, on average, 11.758. So adding one story adds 11.758.
Oh, I see. Okay.
Yeah, that's all this. That's what the question is really asking.
So
Here.
we just answer to that, like if X increased by 1, Y increases by 11.758.
Yes. Now, they're asking it in a way that I really like, a real world
Okay.
interpretation,
So
right? Adding extra story
if one
adds
story
about
is
11
added,
points.
so we will answer like if one story is added, um, the height would change by 11.58.
Yeah, by the height would change by the slope on average.
Okay.
Interestingly, I and J, I don't know if they did this on purpose. I assume they did this on purpose, but I and J are the same question.
Okay. Oh, that makes sense.
Okay.
Asima, did that answer your questions?
Yes.
Okay, cool.
Thank you.
Then let me start on 2-sample and chi-square. And again, you're welcome to stick around and just jump in if you have more questions.
Okay.
What am I doing? New share, 2-sample. So Cole and Hazel, why don't I ask you guys first if you wanted to ask a specific question on these things?
I don't. I think
Yeah.
generally.
Yeah. It's kind of like, I don't know. Like, I don't want to say like, I don't want to say I need like an entire lecture on it, but just like I don't know, just like a simplified rundown, I guess.
Okay, so if we're doing a simplified rundown, then I'm going to skip over questions 1 through 4
Okay.
on the worksheet. Those are sort of an introduction to how the formulas are made, essentially, but are not actually the things that we do ourselves. Right? This was just well, okay, here's how you combine normal distributions, and here's the distribution that you get when you do that, and the standard deviation of that sampling distribution is our standard error, and that's the thing in the denominator. But let me just start from here then, and not worry too much about those things. So if I want to compare two population means, basically the way we actually end up doing that is not this one, because this is a z-test, but is this, the t-test.
Okay.
So we want to do a 2-sample t-test to determine if means are equal. This was the one I was talking about with at the end of ANOVA. And our hypotheses are one of these guys. All of our hypotheses are going to be mu1 and mu2 are equal.
Okay.
And then the alternative is less than, greater than, or not equal to. And again, you just like with the 2-sample f-test that we were just talking about, you could write this as less than or equal to if you wanted right here. Or excuse me, as greater than or equal to if you wanted, because it's opposite of this, but the math will end up being the same.
Gotcha.
So I've just written them all as equals. So we're really checking to see if two population means are equal or not. With the or not could mean that we think one's less, or we think that one's more, or we think that they're just not equal. And so the way we do that is, well, I think we did this one on one of these, and I think Cole and Hazel, you've been here for all of these, right? So
I've been here for number 5.
yeah, that was the one I was going to do. Maybe you could ask me a question from the homework that you were having trouble on.
Number we did it on. Wait. We,
Like on Zoom?
we just did it on number 6.
Yes. Yeah, we did number 6. Yeah.
So if cool one's maybe number 7.
So 7 is 2 prop Z. There's a 2 proportions test, which is.
Yeah, we haven't done it yet.
Yeah, it's true.
Or
We
number
didn't
8.
do that yet. 8 is paired. That one's a little bit different. Right, that one's actually quite different. So I'm happy to do either one of those. Cold, is there a particular one that you wanted to see? Like, was there a homework problem that was giving you trouble, or was there like just an explanation of what's going on when you're doing a 2 sample test that you wanted?
Let's see. You said we already did 6.
Yeah, we did 6.
Wait, when did we do that?
I think last Friday.
On Zoom?
Yeah, it was on Zoom. I think it's recorded. It should be on YouTube.
Was I was definitely in that class, right?
I thought so. I think you've been to all of them.
For some reason I don't have.
Maybe. So we did 2 of them on Friday. On Friday?
Oh,
Yeah.
was it the second one?
Yeah.
Okay, yeah, I didn't go to that one.
Oh, okay.
If it's in that one, then I can just watch the recording on that one.
Yeah, you can just watch the recording where we go over it and talk about it. It's not particularly tough. We end up just using the calculator essentially,
Okay.
and the calculator asks you for S1, N1, and X1 bar, S2, N2, and X2 bar. And you just got to put them in from the problem. And what it's doing is it's doing. Did I write the test statistic somewhere? I must have. Maybe not. Maybe I didn't. It's doing a test using this
The
normal distribution. And it's just finding a p-value. Like, you can do it with normal CDF as well. You just have to calculate all the pieces separately.
Okay.
And then like it uses these degrees of freedom. This complicated number. This is not an integer, by the way. But you don't have to calculate this by hand. Again, it tells you what they are. I should do this all the way through and put this in. 2 sample tests with proportions, roughly the same thing. We're going to check to see if 2 proportions are equal, or one's bigger than the other, or less than, or not equal to. With 2 proportions, you end up doing something a little bit fancier with the math. Did I show that here? No, not really. I just said through clever use of our null hypothesis and some algebra, we can show this. Remember that our null hypothesis is going to be that P1 and P2 are equal. The 2 proportions are equal to each other. And if you do a little bit of fancy math, you can show then that the sampling distribution of the sample differences of proportions has a standard deviation of this, where it uses the combined proportions, which is the combined proportion is just total number of successes out of total number of samples, not for both samples combined. And so you end up with this being your standard deviation, that's the thing in the denominator here. And then the numerator is just the difference between them. Now, that's if you want to do it all by hand. If you want to do it on the calculator, it's very easy, actually. Here, let me just answer 7. I think that would be easier. So the appropriate hypotheses, the null hypothesis is that, whoa, no, I don't want to print, hang on. P1, P-men equals P-women. Alternative is that P-men not equal to. I'll make that not equal to in a second. Right? We just want to say, is there enough evidence to suggest that men and women pass my class at different rates? So we just want to check to see if they're equal or not.
Okay.
That's why I'm using not or not equal to here. All right, so there's my null and alternative hypotheses. PC and QC. So PC is the total number of successes out of the total sample size. So P sub C equals total number of successes, which is 142 plus 129, 142 plus 129, all divided by the total number of samples, which is 213 plus 205, 213 plus 205, which I don't know what that is. Let's see what my calculator says. We got, it's at 271 divided by 418. I'm getting 0.6483.
Divided by. What'd you get?
That 0.6483.
Okay, yeah.
QC is just 1 minus that. QC 1 minus PC minus PC, which is 0.3517.
0.3517.
Yeah. Yep. So the test statistic is that. All right, so it's P1 prime minus P2 prime over the square root of all of that nonsense.
Okay.
So I really want to type that all out. Not really.
Can we
Is it
put
ready?
it in a test?
Yes. So like you might notice that part F is use your calculator to do the same hypothesis test. So we can actually just jump to that if you want to.
Oh, okay.
It's incredibly easy to do. Just go to oh, did I not say to do it in? Oh yeah, stat test 2 prop Z.
Stat test. 2 prop. What's the difference between 1 and 2 prop Z?
Well, one is for one qualitative sample, and the other one is so 1 prop Z is testing to see if one sample has a proportion equal to a number, and 2 prop Z is testing if 2 proportions are equal to each other.
Gotcha.
Like, what do we put for N?
So there shouldn't just be an N. There should be N1 and N2, and
Yes,
X1 and
N1.
X2.
Yeah.
So I've got what, men as 1 and women as 2, or however you want to do it. So then X1 is the number of successes for men, and N1 is the number of trials, right? So X1 would be 129.
Oh,
That's
okay.
the number of
And
successful
N will be
men.
205.
Yeah, and then N1 is 205, and X2 is 142, and N2 is 213. And I think that's all it asks for, and then you just hit enter. And what it does is it calculates all this stuff for you.
Okay.
Okay.
Then we get a p-value of 0.423.
Yeah, something like that's big.
P-value of 0.423.
And
The
so
Z value is minus 0.8.
Yeah, something small. What so what conclusion does that lead you to? Like, do you want to reject the null hypothesis or not?
We'll
No,
accept it.
no, we can accept it.
Yeah. So what does that tell you about whether men or women have a higher pass rate in my class?
It's the same.
Yeah.
Yeah.
Yeah, we have no reason to think that they're any different.
So we're accepting the null hypothesis.
Yep.
Okay.
And the two sample t-test is actually quite similar to that, at least in the sense of like what you're going to do is you're going to get all the information out of the problem and you're going to put it all in your calculator and get a p-value and write a conclusion. And
Okay.
there isn't really much to do by hand, which is
You
kind
just
of how
put it-
modern statistics is actually done. Nobody does anything by hand. You do it all by computer.
Can you go over 8, like pair hypothesis testing?
Sure. So for paired testing, there's a couple different ways to do it. So the number one thing to know about paired testing is that it has two samples, but it's really a one sample test. Because what you're going to do is test to see if your differences are significantly different than 0. That's the idea. And so what you end up doing here, like you can see what I've done here is I put in, this is from this data right here from number 8.
8, okay.
I put in the before and after data into L1 and L2.
Okay.
And then in the header of L3, I did L2 minus L1, right? So you can see out here, and while I'm in the header of L3, I do L2 minus L1 in the header, and it calculates all the differences for me.
Okay.
And the thing I'm checking to see is if those differences are significantly different than 0. So what that means is, from this problem, even though I have two samples, right? I've got a sample from before and a sample from after. I'm not actually using them directly. I'm only using the differences. So like this person right here who started at 206 pounds and then went on the diet and lost 1 pound and is down to 205. That difference is -1. That person lost 1 pound. If they had started at 380 pounds and gone down to 379, that would be exactly the same as far as we're concerned. Right? That's a very different person, right? Much heavier going from 380 to 379, but the difference is still 1. Like we're not actually using these directly. We're only using what the differences are, what the differences between them are. And then when we do that, we're just doing a t-test on the differences. That's it. T-test to see if it's if the differences are significantly different than 0 or not, or in our case, significantly less than 0.
I was putting the data. For
Oh yeah, yeah.
L3, we just use L2 minus L1.
That's what I did,
Yeah.
yeah, because I put after in L2. So I always do after minus before. You can do before minus after. It works okay. It's just a little bit weird because then negative changes show up as positive numbers and positive changes show up as negative numbers. I find this much more intuitive. Like you can see when you do that, you get -1 here because that person lost 1 pound, and you get +2 because that person gained 2 pounds. Yeah, it works the other way around. It's just the meanings are kind of strange.
Okay. For like how do you make a QQ plot? Is it the same thing?
Yeah, we
Or
did. It's the same thing as we did for ANOVA. This shows you how to do that here.
do we do QQ plot with L1, L2, or L3? L3?
So I want to make a QQ plot of the differences. Can I ask you to put that off for a second? I know I did it next year, but let me put that off for a minute because that's
Okay.
actually really just checking the assumptions.
Okay.
Yeah, I should rewrite this actually. But anyway, So if I want to do the paired t-test, what I want to do is t-test on L3.
Okay.
Right, just stat test, t-test on L3.
Just
Yeah. Right, like this guy right here. Stat test, t-test. And the test that I'm wanting to do in this case is, I really got to rewrite this problem. Sorry. The test that I'm wanting to do in this case is whether or not the differences are significantly less than 0. So B. To see if the differences are less than 0 on average. Since negative numbers correspond with a loss. Right, so I just want to go t-test. So I want to do this effectively H naught. I can't do bars here. Oh, I don't want bars. I want mu after.
Mu after is equal to,
Oh yeah,
left it?
sorry, equal to, no, equal to is what for the null hypothesis thing you said is right. Mu before. And then the alternative is that mu after is less than mu before. Right. Ideally, they would have lost weight. Right. That's what we're wanting to see.
Mhm.
Computer, paste, please. Okay.
Is that supposed to be B or is that just B?
I'm sorry. What goal?
Oh, never mind.
Okay. And you can also write these like this if you want to. Before. So if I'm thinking mu after is equal to mu before, then when I subtract them, I would get 0. Or when I did the subtraction here, the thing that I would get would be less than 0. Right? If mu after is smaller than mu before, then when I subtract after minus before, I should get something negative. Right? So you can write your hypotheses either of these ways. I tend to like writing it like this because that tells you what you should do in your calculator for the paired, because you're going to be comparing to 0 and then so you're what am I trying to say here? The mu 0 that it asks you for is 0, and then you're going to want to do less than 0 for the alternative hypothesis. Right, but the way I'm actually thinking of it is like this, but the easier way to put it into your calculator is like this.
Okay.
When you do that, what do you get for your p-value?
Test. We go to test, and t-test.
Yeah.
And do we put from data or stats?
You can do either one, actually.
Um,
I think, yeah, data is probably easier, right? Because it's all in L3.
So what do we put for mu zero? It's just like mu zero.
So that's what I was saying here is I want to write my hypotheses like like this and this, because that tells me what mu zero is. It's this number. It's the number that we are comparing to, which is 0.
Mu zero is 0. Okay. Oh, and we use list 3, right? The difference.
Exactly.
So p-value, we got 0.0881.
Is that all? I thought we ended up rejecting the hypothesis. I'm sorry, what?
0.0881.
0.0881.
Yep.
Okay. Are you sure about that? I'm almost positive we end up rejecting the null hypothesis here. Did you do not equal to?
Yeah, I do. I did not equal to.
Yeah, you should do less than.
Oh. Oh yeah. Okay. Yeah, 0.0441.
Yeah. So at 5%, we would just barely reject the null hypothesis here.
Yeah.
Right, like we're like this is just barely significant to say that that the diet works, which is not great, right? In the real world, you probably want to do another test, probably a bigger one. The other thing that we did in these, or we did in this particular one, was notice that we did a t-test with only 13, with only a sample size of only 13.
Yeah.
Right, which is pretty small. And so we really need to either have a normal population or a large enough sample size, and we don't have the large enough sample size. So we want to check to see if the population is normally distributed. Right, and that's the QQ plot. So that's what.
Oh, okay.
Right, and so if you'd want to do a QQ plot on L3, just like we did for ANOVA. So same thing, right? So stat plot, choose QQ plot, make your data list L3, turn the plot on, graph it, zoom stat. And in this case, you don't get something that's a straight line.
Yeah, we got something like that.
Yeah, you get a giant outlier.
Yeah.
Right? And so this is where you have to think about what you wanted to do in this case. And that's what I asked here, right? One thing I'd like you to think about is, what should we do with the outlier and why? Right, so here's what I did. Like this is the original QQ plot I got. And then what I did for this one was I just deleted it. I just took out the outlier and said, all right, well, I'm just going to delete it and see what it looks like then. And that's what I did. And I got this. And so the question I really have is, should we leave in the outlier or should we take it out? And how do you make that decision? Right, and so if we look at the outliers here, or if we look at the data here, it's pretty obvious which one the outlier is. Right? It's this guy who lost 52 pounds.
Yeah.
Right, of all of the combined total weight loss, he had like half of it.
Yeah.
Like half of the weight was lost by this one guy. And so the question is, should we leave that in or take it out?
We take it out.
Why?
Because it's an outlier. Like it's not normal.
It's different than the other things, but if we're testing to see if this diet works, and this guy followed the diet, right? Why? Like I would want to leave it in that case.
Yeah.
You could make a couple of cases. You can make a case for whether we leave it in or take it out, depending on how you want to do it. I think the best answer to that question of leave it in or take it out is do both. You should do do the test once with it in, and do the test once with it out, and see if it changes things. If things don't change that much, then it doesn't really matter which one you do. And if things change a lot, then it does matter, and you can decide, well, okay, maybe this guy is different somehow. Maybe the fact that, so he was by far the largest person in the study, right? Like 50 pounds
Yeah.
heavier than anybody else, or maybe just 30 pounds, but whatever. He's the biggest guy in the study. So this is an instance where outliers are really interesting. Very often, like the most interesting thing in your data is outliers. And this is one of those cases where maybe that's super interesting, where like for everybody else, they all lost 1 or 2 pounds. You know, some people lost 9 pounds, some people gained 2, but the results were fairly modest for something that lasted 6 weeks. But for this guy, they were not modest, right? And so we would want to find out why this particular guy lost so much weight, right? So this would be an instance where you should probably do both, but I think I'm inclined to I'm really inclined to do both. Like I like leave it in, and I also like take it out just to say, okay, well, for people who were less extremely overweight, look at this. The test looks great, right? The data is nice and straight, or the QQ plus nice and straight. Everything else looks fine. When you do it, you actually get a smaller p-value when you take him out, which seems really strange if you think about it, but that's how it works out. And so you would be even more sure that it caused people to lose weight without him in there. And then the data looks more normally distributed too. So if I were like writing up my results for this, I would say, okay, here is my test. Here are all the differences. You can see this one is a big outlier. Here's what we get when we do it with the outlier in. We get this p-value of 0.044. Pretty small, or just small enough to reject the null hypothesis. It's smaller than 0.05, but just barely. And then here's what we get when we take out the outlier and decide, okay, why there's probably something different about this guy. I don't know what it is, but there seems to be something different about how the diet affected him. So when I take him out and do the analysis, here's the thing I get. And we actually end up getting an even smaller p-value. And so your conclusion would probably be, this data or this diet does seem to work, although it doesn't cause people to lose a lot of weight. It does seem to help them lose weight if they follow it. If we include that, people over 300 pounds, we get this one extra guy and we get a slightly different result, but the conclusion is still roughly the same.
Okay.
So something like that. This is a very nuanced kind of question. It's not obvious to figure out what to do here, but that's what I would do. I would do both. Sorry, go ahead.
Like in my calculator, if we go to plot 1, then type an X list and Y list.
So if you have an X list and a Y list, then you have not selected the right thing. So like you see how, so you should only have something that says data list. You have to be on this 6th picture right here to get that. It'll change these things depending on which picture you're on. So if you have an X and a Y, you're probably looking at the first picture. You wanna go down to type and then switch it to this guy.
Okay, good.
So for the last question, it's still the same, right? Because we just do a t interval. We just write down the answers we get from the t-test.
Right,
T
exactly.
interval.
Yeah, you're just doing a regular old t confidence interval for the differences.
Yep. Okay. So do we have to write a conclusion for the confidence interval too?
It's always good to interpret, right? I would say something. So did you do one of those?
Yeah, I did already. It says like minus 15.72, 1.259, 1.286.
1.259? Not negative?
Yes. Like negative.
Oh yeah. No, you're right.
15.72.
You're right because it's two-sided, huh? 1.259.
Yep.
This diet. Say 6 weeks, I think. 6 weeks. No. I don't know. I said that wrong. That the average. Six weeks. Between a 15.72. Six. Something like that.
Okay.
Yeah, I guess that's what I'd say. Seema, were you able to get the QQ plot working?
Yeah.
Okay.
So like for this two sample only, and also for the ANOVA, like QQ plots are also just for testing, checking.
Yeah, they're just to check to see if your data is approximately normally distributed.
Okay.
Yeah, that's what QQ plots do.
Jeff, when are we getting our tests? Like it's this weekend or next weekend? Next weekend.
It is the 1st, so it's next weekend. We've got a week for ANOVA, and then whatever leftover time you have is for review. So this week until Wednesday. It's Wednesday, right?
Oh, so we have another chapter for ANOVA?
No. ANOVA is the last thing. We have a week.
Okay.
We have a week to work on ANOVA, right? We just learned it today.
Yeah.
You have a week
Okay.
to work on that, and then the homework will be due next Wednesday, and then you get the test on Friday, I want to say.
Okay.
Is that whatever May 1st is, Friday or Saturday? I think it's Friday.
Okay.
And then I want you to have it back to me by Sunday.
Okay.
And then I'll post the final on the day after that. Which reminds me,
Okay.
I should post all of the hypothesis testing review worksheets I have for you, which there are a couple. Nothing. Okay. So we are at 2 hours and 6 minutes so far.
Yeah.
Or 2 hours and 7 minutes so far. So can I ask you guys? So I tell you what, let's do another extra Friday session.
Okay.
Where you guys can ask whatever ANOVA questions you want, and if you still have some on chi-square, we can maybe do some chi-square then too.
Okay.
So let me schedule something for Friday at
whenever you're
last
okay.
time 5 o'clock.
Okay.
I think that was what people said they could make. So let me do Friday at 5 o'clock. I'll send out an email today in just a minute here, and I'll make a new meeting then.
Okay. Thank you.
Cole, does that work for you?
That's perfect. Thank you.
Okay, cool. We'll do that then. All right, good deal then. I'm going to unshare here.
Yep.
And just say thank you guys for coming. And I'm going to end the meeting now, and we'll see you. I'll post this on YouTube in just a couple of minutes once it finishes downloading and processing. And then you guys can look at it there if you want to see more. And then if you have more questions on anything, we'll set up a Friday meeting at 6 o'clock or at 5 o'clock. Yeah. All right.
Thanks, Jeff.
Thanks, guys.
Bye.
Bye.